Oh, wow. The front row is a lot more populated these days. Welcome back to the land of the living, you guys. Yeah, it feels like almost like we have a full class today. Yeah. Everybody's back from quarantine. This is great. So I got my round of emails telling me that all the students have come out of quarantine on Saturday. And I got another round of emails on Sunday telling me like a bunch of other students were quarantined. So yeah. Fun stuff, fun stuff. But if you're going to quarantine, I would say that these last 2 weeks are probably the best because, well, as long as you don't have any labs to make up. If you do, you're kind of screwed. No, I'm just kidding. For all of you people who are still quarantined, don't worry, we'll figure something out. You're welcome, Brenda. Okay, you guys have a good weekend? Yeah? Doesn't seem like it. Or maybe you had a great weekend and you're just kind of sad to get back into the swing of things. I had a pretty good weekend. Notre Dame. Do you guys watch football at all? Notre Dame, which is, I went to grad school at Notre Dame, so I have a bit of a connection with them. But anyway, they beat number 1 Clemson. That was a pretty exciting game. I didn't actually watch the game. I heard about it later. I'm not that much of a football fan, so I heard about it later, and then I went on YouTube and watched the highlights. That's about my level of involvement in terms of football. I'll watch the highlights. Okay, let's see here. Oh, I do have something to say. I had a few people ask me if I could extend the deadline for the homework because having the weekend to do it didn't seem like enough to be able to do that. So I went ahead and extended it to Wednesday. So it said that it was due Monday this morning at 10 a.m. up until about 45 minutes ago. And then I extended it to Wednesday. So if you guys want to continue working on that homework, so if you've already submitted and you want to continue working on it, like you can resubmit another homework up to Wednesday at 10 a.m. Okay, so I've extended that. I'm going to publish chapter 9 homework today, right after class, and we may finish chapter 9 today, I'm not sure. But I'll publish the homework today, and then we can continue working on that for the rest of this week. It'll probably be due next Monday. Okay? Okay. That's it for administrative stuff. Right off the bat today, I'm going to have you guys do a bit of work. Okay? So I want you guys to come up with the Lewis structure for ozone. And let's give about 3 minutes to this exercise. You guys go ahead and come up with a Lewis structure for ozone, and then we'll go through it together. Okay, so who came up with a structure that looks something like this? Raise your hands if anybody did. No? No? Really? You did. Okay. Nice. Thank you. Who came up with, or if anybody came up with, a structure that looks like this? Anybody? Bueller? Takes a little bit of time to get the brain greased and ready for the day. I understand. It's been a long weekend. Nobody? Okay. So the reality is you could have drawn either of these structures and they both would have been valid, but they're different structures. Where is the double bond located in this Lewis structure? Is it located on the left side or is it located on the right side? Let's go through the whole process of actually writing up the Lewis structure for this molecule first. Okay, so what's the first step? First step is forming the skeletal structure. Okay, so the skeletal structure in this case is super easy because they all have the same electronegativity, and so we can just put them all in a line. Okay, so 1, 2, 3. That's the skeletal structure for ozone. The next step is to count up the number of electrons. Okay, so we have 3 oxygen atoms here, and each of these oxygens contribute 6 valence electrons. So we have 3 times 6, 18 electrons. Okay, the third step is distributing these electrons within that skeletal structure. So we redraw our skeletal structure here. And what we do is we go first in between the atoms, right? So we want to put electrons first in between the atoms. So we have 2, 4, okay? Now all we have left are basically non-in between the atoms, and we start on the terminal atoms. So we start putting these lone electron pairs on the terminal atoms first, and then we move to the central atom. Okay, so we have 2, 4, 6, 8, 10, 12, 14, 16. So we've used up 16 electrons so far. We have 2 more, and they go, now we move into the central atom, and we place those lone electrons on the central atom. Okay, we've used up all of the electrons at this point. And as you can see, the central oxygen atom only has 6 electrons surrounding it. Okay, so we only have 6 electrons there. This is breaking the octet rule, and it's no bueno. So we need to donate a lone electron pair from one of the terminal atoms to form a double bond. But the question is, which side? Which side do we go with? The answer is you can go with either side. They're both equally energetically favorable, but the reality is you can form a double bond with both sides, okay? This is called a resonance structure. So we can form 2 molecules here. Okay, we can form either of these 2 molecules, and the reality is that actually this molecule exists as kind of a mixture of both of these. Okay, it exists in reality as a mixture of both of these. So really, the way that it looks is something like this. We have a partial double bond between each of the oxygens. Okay, this is called a resonance hybrid structure. Okay, there's a resonance between these 2 sides being a true double bond, and so what you end up with is both of these bonds have somewhere between a single bond and a double bond nature. And you can measure this by looking at the bond length for these molecules. Right? If you have some measurement that enables you to look at the bond length between atoms in a molecule, you could plug this into this measurement and see if it was double bond on one side and single bond on the other. you would see two distinct bond lengths coming out of this experiment. But when you do this experiment, what you find is one distinct bond length that's kind of in between what you would expect for a single and a double bond. Okay, so this is where we know that this resonance structure is actually occurring. We have something that's kind of in between a single and a double bond, and it's called a resonance hybrid structure. Okay, and in this case, remember back in the quantum mechanics lecture, we talked about how the electron exists as kind of a probability density. Okay, so think of that in this way. The electrons that are involved in these double bonds are said to be delocalized over two separate bonds. Okay, so they can exist. They have a probability density that extends over two bonds. Okay, so this is electrons are delocalized. Okay, they're delocalized over both bonds. You don't have one bond or the other. There is a delocalization of these electrons over both bonds. And in effect, this lowers the energy of the molecule. Okay. And if you've been following the trend, whenever you lower the energy of something, that's the way it likes to exist. It likes to exist as the lowest energy possible state that it can actually come into. Okay, so any chance that something has to lower the energy, it's going to take it. And that's why ozone exists as this resonance hybrid structure. Okay, this delocalization actually stabilizes the molecule. Okay, yeah. What's up? Can you go back a sec? Yeah. Yeah. Oh. You mean like this? Okay, that's a little awkward. So in principle, you could draw it this way, the skeletal structure, but it's going to start to break down when you use Lewis theory like you should. Lewis theory only allows for placement of atoms at the ordinal directions. It doesn't allow for half directions. So in this case, we would have to form a bond that's kind of at a triangle, right? And Lewis theory doesn't allow for that. It says that everything is placed at the ordinal direction. But in the next couple of chapters, we'll get into some different theories where something like this could definitely be possible. Okay, so this type of molecule can exist, not with oxygen, but with other species. And the shape that they take is dependent on a different set, and it's explained by a different theory. Okay, so once you get a little bit complicated in terms of molecules, Lewis theory breaks down, which we're going to see actually in just a little bit. Towards the end of this chapter, we're going to talk about where Lewis theory fails. Okay, interesting question though. Okay, let's do another example where we see this resonance structure. What about the nitrate ion? Okay, oops. Okay, let's look at the nitrate ion. In this case, when we form our skeletal structure, we're going to put the most electronegative elements towards the outer part. Okay, so they're going to be terminal. That's our rule for these skeletal structures. So that means that nitrogen needs to be in the middle. Okay, so we have a skeletal structure that looks something like this. Next, we need to calculate the number of electrons. So we have 5 electrons from the nitrogen and 6 electrons from each of the oxygens. So we end up with 5 plus 3 times 6 is equal to 24 electrons. Okay, so these are the number of electrons that we have to distribute throughout this molecule. And then the third step is to place these electrons about the molecule. Okay, so let's go ahead and write the skeletal structure over again. Okay, now we have 24 electrons that we can use up. So let's do the ones in between the atoms first. Okay, so we need to form the bonds first. So 2, 4, 6. So we've used 6 out of 24 here. Okay, 6 out of 24. Now let's fill in the rest. So the rest get filled in by filling out the lone electron pairs on the terminal atoms first, and then coming back to the central atom. Okay, so let's fill these out. Let's see, we have 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so we've filled out there. Now, just in the case with ozone, we have one in the middle, this middle atom it only has 6 electrons around it, okay? So it's not satisfying the octet, it's not so happy, but everything on the terminal is happy. So what do we do when this happens? We move in a lone electron pair to form a double bond. But you can see, again, we have the same conundrum that we had with ozone, where we can move a lone electron pair from any of these oxygens in to form a double bond. Okay, does everybody see that? You can move a lone electron pair from any of these oxygens in to form a double bond, which would make nitrogen happy, and it would make the oxygens happy. Okay, so we have 3 structures that we can possibly make here. We can move this guy in. Oops, not to there. We can form a double bond. We can form a double bond, or we can form a double bond. Okay, so we can form a double bond at each of these axes. So the 3 structures that we're going to get out of this are something like nitrogen, oops. Okay, so we'll get something like that. And by the way, I forgot to add in the electron because this is a negative species, right? So I should have had a +1 here. Right, this is a negative ion, so we should add 1 electron because it's a negative ion, and it still equals 24. So we have 18 plus 6 is 24. I just skipped a step. Okay, so we have 1 extra electron in here. Okay, so we can form this structure that looks something like this. So we have nitrogen, double bond oxygen with some oxygens coming off here and here. Okay, so we can form that. And of course, since this is an ion, we need to put it in brackets and say negative on the outside of the bracket. So we can have this structure, or we can have the structure where the double bond comes to the oxygen at the top. Okay, and everybody's still happy here. Or we can have the case where the double bond goes to the left. Okay, so we can have these 3 possible structures that we can form with the nitrate ion. And you probably can guess what we're going to do next. We're going to form a hybrid resonance structure, just like we did with ozone, okay? So in reality, these 3 things kind of average together, and we get delocalization of these electrons over these 3 bonds now. So we have a resonance hybrid structure, which looks something like this. We have nitrogen, and we have partial double bonds between all of the oxygens. Okay, so this is the resonance hybrid structure of nitrate, which is closer to reality. This is how this thing exists in reality, rather than being one of the others. Okay. So that's resonance hybrid structures. You'll probably see a few of those in your future, right? So pay attention when you're making these structures and see if you could possibly form a resonance structure. So always be aware that this is a possibility, because this is more correct of a structure than the single case where you just have one location with a double bond. Yeah. So in the when you're actually writing out the this guy here, it's hard to put in the lone pairs because those are the ones that are also contributing to that double bond. Okay, so typically when you write the resonance hybrid structure, you don't put the lone pairs in because it's ambiguous. Okay, so the best way to write this in terms to be completely unambiguous is just to have these three structures written, just like I have here. Okay, so this is the correct answer to a question, what's the Lewis structure of the nitrate ion? Okay, you have to give all possibilities and say it's a resonance structure. Okay. Okay, so that's resonance stuff. It'll happen, you'll see it. Okay, so keep that in mind when you're forming these Lewis structures in the future. Yeah. What's that? No, because that's just the mirror image at the top. Yeah, it's the same structure. So for you, those of you online, it was just asked if we need to also include the structure where we have something like this, rather than the oxygen being on the top. No, you don't need to do that. This is the exact same structure. That's the exact same structure as what we just did above. It's just mirror imaged. Okay, so you don't need to worry about doing all possible permutations of the same thing. You good? Okay. Okay, so here is a point at which we start to see Lewis structure kind of breaking down. Okay, it's not so obvious what we're going to do next when we start having these issues with resonance. So we need to introduce a new piece of Lewis theory that allows us to disambiguate between possible structures and say which is the best structure. Okay, because there are many different ways that you can form a valid Lewis structure that obeys the octet duet rule, but is not necessarily the lowest in energy. Okay, so we need a way to basically look at all of the structures we formed and say which one is the most likely. Okay. We're going to do this with something called formal charge. Okay. Formal charge is simply a bookkeeping method. Okay, it's simply a bookkeeping method to figure out if a Lewis structure is valid or not. Okay, that's all it does. It is not the actual charge on an atom. I can't make this point enough. It's not the actual charge. It is simply a tool to determine if a Lewis structure is valid or not. It has no bearing on reality. It's just a nice bookkeeping tool. Okay, it's just a fictitious number that we're coming up with. So formal charge, I'm going to call it Fc, is equal to the number of valence electrons on an atom. So for example, oxygen has 6 valence electrons, minus the number of non-bonding electrons. Okay, so if it's we're talking about single atoms here, you calculate the formal charge for single atoms. So for example, if this oxygen that we're talking about has 6 valence electrons, and let's say it has 2 lone electron pairs. Okay, these lone electron pairs that aren't doing any bonding, these are non-bonding electrons. Okay, so the number of non-bonding electrons here would be 4. Plus 1/2 the number of bonding electrons. And the bonding electrons are the ones that are included in the bonds. Okay. Let's do an example. If we look at hydrofluoric acid, HF, okay, HF has a Lewis structure that looks like this. We have H and we have F Okay, this is the Lewis structure for HF. Let's calculate the formal charge on each of these atoms. So the formal charge for the H would be equal to, there's one valence electron from hydrogen, right? It's always one, minus the number of non-bonding electrons. There are no non-bonding electrons on hydrogen. There are never non-bonding electrons on hydrogen. So this is 0 plus 1/2 times the number of bonding electrons. In this case, there are two bonding electrons. Okay? Each of these electrons here are bonding with electron, or are bonding with hydrogen. Okay, so there's two here. That looks like a sideways smiley face. Okay, so 1 minus 1 is equal to 0. Okay, so formal charge on the hydrogen in this case is 0, and the formal charge on the fluorine is equal to 7. There's 7 valence electrons around fluorine, or fluorine has 7 valence electrons. And then we subtract from that the number of non-bonding. In this case, fluorine has a significant number of non-bonding. There are 6 non-bonding electrons surrounding fluorine, plus 1/2 times 2, which is the number of bonding electrons that fluorine has. Okay. And again, this is 7 minus 7, so we equals 0. So in each case, the formal charge for this structure, for each of the atoms in the structure, is 0. Okay. But formal charge does not equal actual charge. Okay, remember this. If you look at the partial charge distribution on this atom, or on this molecule, you have hydrogen and fluorine, and the electron density is significantly more dense around fluorine than it is hydrogen. There is this huge amount of electron density over here, and very little around the hydrogen. Okay, this is a polar bond with a dipole pointing towards the fluorine. Okay. So, formal charge is not telling you the actual charge of an atom. The actual charge of the atom is very different from 0, right? There's a little bit of positive charge on hydrogen, and there's a little bit of negative charge on fluorine. It's not 0. Formal charge is simply a way to tell if the Lewis structure is stable or not. Okay? So, what are some rules for formal charge? Because at this point, we don't know if 0 formal charge is reasonable or if it's not unreasonable. Okay, so let's set some ground rules for formal charge. The first rule is that the sum of all formal charges for a neutral molecule must be 0. Okay, so when you sum up all of the formal charges for a neutral molecule, it must equal 0. Rule number 2, the sum of all the formal charges for a ion must equal the charge of the ion. Okay, for example, nitrate, NO3 minus. The formal charges for all of the formal charge for all of the atoms, the nitrogen and each of the 3 oxygens, must sum up to -1. Okay. Rule number 3. Small formal charges are better than large formal charges on individual atoms. Okay, so small formal charges are better than large formal charges on individual atoms. And the fourth rule, sometimes formal charge is negative, and in this case, the negative formal charge must reside on the most electronegative atom. Okay, so the negative formal charge must reside on the most electronegative atom in the molecule. Okay, and this is only true when formal charge can't be avoided. Okay, only when formal charge can't be avoided. So by reading these rules, you can come to the conclusion that the smallest formal charge possible for each individual atom is the best possible Lewis structure. So having a formal charge of 0 is perfect. That's where we want to be. And if we have any formal charge in the molecule, it should be minimized. Okay? It should be minimized. Let's look at an example using our new rules here. Let's look at hydrogen cyanide. Which is HCN. Okay. CN is the cyanide group, and it's attached to hydrogen cyanide. Okay. If we look at the Lewis structure for hydrogen cyanide and we go through the process of forming this Lewis structure, you will find that there are two possible structures that you can form. Okay. We can form, we're going to call this side A and this side B. We can form the structure H, single bond carbon, triple bond nitrogen, lone pair. Okay, so this satisfies the octet rule, but we can also form H, single bond nitrogen, triple bond carbon, double bond, or lone pair. Okay, both of these structures are valid in terms of their octet duet, like they satisfy the octet and duet rule. But now we want to apply the rules of formal charge to these and see what we can learn from this. Okay, so over here I'm going to write the number of valence electrons minus the number of non-bonding electrons minus 1/2 the number of bonding electrons. Okay, so for each of these I'm going to write underneath them what their valence electron is, their bonding electrons is, and their non-bonding electrons is. And then we'll sum them all up down at the bottom. Okay, so hydrogen has 1 valence electron, carbon has 4 valence electrons, and nitrogen has 5. That's the same over here, 1, 5, 4. Okay, now, how many of bonding electrons does hydrogen have? Hydrogen has, non-bonding electrons. Hydrogen has 0 non-bonding electrons. Carbon has 0 non-bonding electrons, and nitrogen has 2. Okay. Does everybody see that? Over here, there's a lone pair on this nitrogen. That's a non-bonding electron pair. Both of those electrons are not bonding to anything. They're just kind of floating in the void. Okay, so these are non-bonding electrons. Next, we need to take away 1/2 of the number of bonding electrons. So for hydrogen, hydrogen has 2 bonding electrons. It has a bond right here. And remember that bond, each of these lines represents 2 electrons that are being shared. So hydrogen has 2 bonding electrons. Take 1/2 of that is 1. So that's -1. Carbon has 2, 4, 6, 8 bonding electrons. Take away 1/2 of that is 4. And nitrogen has 2, 4, 6 bonding electrons. So take away 1/2 of that is -3. We'll add all of these up. We get 0 for the nitrogen column, 0 for the carbon column, and 0 for the hydrogen column. So this is a pretty happy structure. It satisfies octet and duet rule, and the formal charges on each of the atoms are minimized. Let's see what happens with the other structure. So in this case, we have the number of bonding electrons on hydrogen is 0, again. The number of bonding electrons on nitrogen this time is 0. And the number of non-bonding electrons on carbon in this case is 2. Okay, so we have -2 there. Next, we come down to the bonding electrons. Hydrogen minus 1/2 of the bonding would be -1. There's 2 bonding electrons there. For nitrogen, it has 8 bonding electrons, so this would be -4. And for carbon, it has 6 bonding electrons, so this would be -3. We add all these up together, and we get 0 for hydrogen, +1 for nitrogen, -1 for carbon. So which of these structures is the most stable Lewis structure? A. A is the most stable Lewis structure because we've minimized the formal charge. Over here, you have a couple that have formal charge that are non-zero, which sometimes can be okay, but only if this is the minimal possible value. Okay, so we found the minimum possible value is 0 in all cases, so A is the best structure. Okay, A is the best structure. Let's do another example, again with cyanide. Okay, let's look at the cyanate ion. So this is OCN minus, okay? This is cyanate, okay? If we come up with a Lewis structure for cyanate, we can come up with, we can draw several different examples. Let's call, well, I guess we won't give them names. Let's do this structure first. We can have oxygen over here with a bunch of lone electron pairs bonded singly to a carbon, and then the carbon has a triple bond to the nitrogen, which has a singular bond. This is of course a ion, so let's put it in brackets. Okay, that's one possibility. We can also have oxygen with 2 lone pairs double bonded to a carbon. Carbon is double bonded to a nitrogen, and the nitrogen has 2 lone pairs. Okay, that's another possible structure that you can form. And then lastly, we can have oxygen with a single lone pair triple bonded to carbon, single bonded to nitrogen with 3 lone electron pairs. So now you can see we haven't changed the positioning of the oxygen, carbon, and nitrogen in either of these cases. All of these have the exact same skeletal structure. Okay, we have the most electronegative stuff out to the sides, and we have the least in the middle. Okay, so this is the correct skeletal structure, but we have 3 possible compounds that we could form, and we have no idea which of these is the correct compound, or at least the best compound. So in this case, it's very useful to use formal charge to figure out which of these is the best. Okay, so over here, I'm going to write number of valence electrons, just like before, and then number of non-bonding electrons, and then number of bonding electrons. Okay, so for oxygen, oxygen has 6 valence electrons, 6, 6, 6. Oof. Carbon has 4 valence electrons, so 4, 4, and 4. And nitrogen has 5. The number of non-bonding electrons for oxygen in the first column is 6. So we have -6 here. The number of non-bonding for carbon is 0, so -0. And then the number of non-bonding for nitrogen is 2. So we have to take away 2 here. Next, we need to subtract the number, half the number of bonding electrons. So in this case, the oxygen has 2 bonding electrons. Half of that is 1, so this is -1. Carbon has 8 bonding electrons. Half of that is 4, so -4. And nitrogen has 6 bonding electrons, so half of that is 3. So we have -3 here. And in this case, we end up with -1, 0, 0. Okay, So let's see how we can do with the other structures. In this, in the middle column, oxygen has, let's see, 4 non-bonding electrons. Carbon has 0 non-bonding electrons, and nitrogen also has 4 non-bonding electrons. Oxygen, in terms of bonding electrons, oxygen has 4, so we need to subtract 2 there. Carbon has 8, so we need to subtract 4. And nitrogen has 4, so we need to subtract 2. So we end up with 0, 0, -1. Okay, so far so good. Let's check the last one. In this case, oxygen has only 2 non-bonding electrons. So -2 here. Carbon has 0 again, and nitrogen has 6. Okay, now in terms of bonding electrons, oxygen now has 6 bonding electrons, so half of that is 3. Carbon has 8, half of that is 4. Nitrogen has 2, half of that is 1. So we end up with oxygen having a +1. Carbon having a 0, and nitrogen having a -2. Okay, let's quickly sum up the formal charges and make sure that they follow the rule for formal charges that it has to equal -1, because remember, this is an ion. The sum of all of these formal charges for all of the atoms has to equal the charge of the atom. That's one of our rules. So let's go ahead and make sure that that is true. So the sum of the formal charges in this case is equal to -1. Good. That satisfies. In this case is also equal to -1. Good. That also satisfies. And in this last case, also equal to -1. Good. So they all satisfy this rule. Okay. So they're all valid structures. But let's look a little bit closer at which atoms have the formal charges. Okay. So if we go back up to our rules, we want the negative to be on the most electronegative. And in this case, it's reversed. Oxygen is more electronegative than nitrogen. It's closer to fluorine, remember, it's closer to fluorine. Closer you get to fluorine, the more electronegative you are. Okay, so oxygen is more electronegative than nitrogen. So this is a bad structure because it has the negative formal charge on not the most electronegative. Okay, so out of these 3, we can whittle it down to these 2 as being the best. Okay, so these are better. Okay. Now, out of these 2, which one is best? So again, we can use the same rule. In the middle column, the nitrogen has the -1. In the other column, the oxygen has the -1. We know that the most electronegative atom always wants to have the lowest formal charge or the most negative formal charge. So in this case, out of these 2, this one on the far left is the best. Okay, it's the best. So the best structure for the cyanate ion is this. However, we need to recognize that this is also going to be a resonance hybrid structure. Okay, you can have a resonance between all 3 of these possible states, but the one state that's going to contribute the most to the hybrid structure is this one here. So this one contributes the most. Okay. So we're not saying that this is how the molecule exists. We're rather saying this is the most likely version of the resonance. This is going to be the most, I guess, the nature of the hybrid structure is going to be mostly determined by this structure itself. So the hybrid structure is going to look pretty similar to this, but there's going to be some double bond and triple bond character here as well. Okay. We need to keep that in mind, but this structure is definitely the most favored. Okay, so that's how you use formal charge. It's very useful. I recommend you use it whenever you form a Lewis structure. Okay, just calculate the formal charge on all the atoms. Make sure you're not making a mistake somewhere. Okay, so Lewis theory is pretty good. For how simple it is, it's pretty good at predicting how things are going to bond. But there are certainly places where it starts to break down. The more and more complicated you get, as you know, molecules can be extremely complicated. The more complicated you get, the more it's likely to break down. Okay, so there are some exceptions to Lewis theory. In the form of exceptions to the octet rule. Okay? The first exception is odd electron species. If you have a molecule that has an odd number of electrons, I don't know if you've noticed up to this point, but all of the molecules we formed have had an even number of electrons, which is very easy to put around in a molecule if you're doing it pairs at a time. Okay? But if you have an odd electron species, which is very possible, then you have a problem. Okay, and these are, of course, molecules with an odd number of electrons. The second exception are called incomplete octets. And this is where a system doesn't have enough electrons to form a full octet. And the third exception is called an expanded octet. Okay, let's go through each of these individually, starting with odd electron species. So odd electron species, you guys are probably most familiar with these as being called free radicals. Odd electron species are free radicals. Okay, and they tend to be very reactive. And because of this, they're dangerous to your health. So if you ingest a lot of free radicals, or if you breathe in a bunch of free radicals, it's very dangerous because these things are likely to interact with other things in your body and kind of mess you up in some unknown way. I don't know how they actually work, but they do. They're bad for you. Don't eat them. You've been warned. Okay, so let's look at an example. Nitrogen monoxide. You guys saw this in the lab, and it even looks bad for you, right? You see it and you're like, okay, yeah, I don't want to breathe that stuff in. Okay, that's your mind telling you, yeah, bad stuff. If we look through the Lewis structure, we see that there is an odd number of electrons here. Oxygen has 6, nitrogen has 5, so we end up with 11 electrons. How do you distribute those along with the Lewis structure? So it turns out that the best possible structure you can make is nitrogen double bonded with oxygen like this, where we have a lone electron pair on the nitrogen, but also a lone electron all by itself on the nitrogen. Okay? This doesn't happen very often, but when it does, use formal charge to figure out which one should have the lone electron or the other. Okay, so use formal charge, and you can kind of move that lone electron around until you find a good spot. Okay. Notice that the octet rule is not met. So we have 7 around the nitrogen and 8 around the oxygen. Okay, so this breaks the octet rule, yet it still exists. Nitrogen monoxide exists. You guys have seen it in the class. Okay, in these cases, just write the best possible Lewis structure using formal charge. Okay. The second exception to the octet rule are called incomplete octets. Okay, and these are formed from some compounds which don't have enough electrons to actually form an octet. For example, BH3. How many electrons can we have in this case? The total number of electrons is 6. Okay, we don't even have enough electrons to form an octet. And yet BH3 exists. Okay, the best possible Lewis structure we can come up with looks like this, where the hydrogens all satisfy the octet duet rule, but boron does not. Now it turns out that boron tends to form these 6 electron molecules. Okay, so boron tends to form these molecules that have only 6 electrons. So it's breaking the octet, but in this case, it is kind of an expected thing, and it still exists. Okay, so this is an exception to Lewis theory. Another example. Boron trifluoride. Okay, again, boron only has 6 electrons around it. It is not following the octet rule, and yet it still exists. You could say, why not move one of these lone electron pairs in to form a double bond, right? This would be your first inclination if you were to look at this structure from a Lewis perspective. So why not move this in and form a double bond? If we look at the formal charge, we see that this is crazy, okay? So in this case, if we have boron, double bond fluorine, fluorine, and fluorine, and we calculate the formal charges for all of these things, we find out that boron has a -1 formal charge in this case, and fluorine has a +1, which is a big no-no because fluorine is the most electronegative compound, and it never, ever, ever wants to have a positive formal charge, okay? So formal charge in this case gets really wonky, and when it gets really wonky like this, we say, okay, it probably doesn't form that. It's only going to form the incomplete octet with boron because we know that boron tends to form this. And indeed, this is the better structure, even though it breaks the octet rule. So we're starting to push the limits of Lewis theory. Basically, we've come to a point where Lewis theory is just too simplistic to be able to go any further. It gives us a good idea of where to start, but it can't go beyond that these more complicated molecules. And the next 2 chapters will introduce new theories to be able to explain why this kind of stuff happens, why we have incomplete octets, what is happening with free radicals, etc. The third exception to Lewis theory is called the expanded octets. Okay, so I know that you are just burning to know what an expanded octet is, but we are at 11:03, and it's going to take me more than 2 minutes to explain this. So let's break there. We'll come back on Wednesday. Don't forget, if you've missed quarantine labs in the last couple of weeks, or even in the first couple of weeks, if you have a lab to make up, make sure to let me know when you're going to be coming this week to make that lab up. Okay? Awesome. Have a good Monday.